Hi everyone, my name is Ajay. I'm a PhD student at MIT working with Professor Saman Amarsinge, and today I'll be talking about an exciting new methodology for developing high-performance DSLs or domain-specific languages when you have very little or no compiler knowledge. To start with, let me talk about why DSLs are important. In our years of building and working with compilers for various performance-critical domains, we have observed that for obtaining high performance, one has to apply optimizations that make use of some domain knowledge. For example, when working with a domain like image and video processing, one would have to combine complex transformations like operator fusion, tiling, vectorization, etc. At the same time, when working with a domain like graphs, one would have to optimize for load balancing, direction of iteration, and deduplication to better adapt to the inherent sparsity in the graph data structures. Finally, for a domain like sparse array programming, we would have to deal with code generation for various data layouts for tensors and sparsity patterns. Previously, individual DSLs such as Halide, GraphIt, and Taco have been built for these exact optimizations and are currently widely used. The common pattern here is that these DSLs are built for use by domain experts and also in collaboration with domain experts. This means that developing these languages and their compilers still requires significant contributions from compiler experts like us. Ideally, we would want to be in a world where these DSLs are built by domain experts completely on their own. Today I'll show you how to achieve this goal using our framework BuildIt. Before we get into how we use our framework to build high-performance DSLs, let us look at what are the typical steps when writing a DSL compiler the traditional way. For any language design, the first and the foremost step is to understand the domain and the kind of programs that are written, and come up with an abstraction that captures all the programs in the domain. If you have ever written a library for a class of problems, this step would be analogous to coming up with an API for your library. Typically, the next step is to implement a parser and other infrastructure like an IR or intermediate representation to represent the program inside the compiler. Following this, we implement all the domain-specific analyses and transformations inside the compiler to obtain the most optimized version of the input program. Finally, we implement device-specific code generation to be able to run the programs on CPUs, GPUs, or any other domain-specific accelerators. If you look carefully at this, you'll notice that 3 of these 4 steps actually require a lot of compiler expertise. At the same time, the domain experts are very well equipped for the first step of coming up with an abstraction because they understand the domain and implement high-performance libraries all the time. Our goal would be to automate these 3 steps in such a way that domain experts can create compilers by just implementing library. Before we answer how to do that, I would like to remind everyone about what BuildIt is and how it works. BuildIt is a lightweight multi-stage programming library in C++. In traditional single-stage programming, we write a program that we pass through a compiler to obtain an executable. We run this executable with some inputs to obtain the final output. In multi-stage programming, on the other hand, the output of this compiled executable is once again another program that we can compile and execute with a new set of inputs to obtain another program. This process can be repeated as many times as we want before obtaining the final output. This kind of an approach lets us generate a partially valid program that is tailored to a certain set of inputs and is typically more optimized than the general one. BuildIt uses the type of the variables and expressions to decide the stage in which these expressions will be evaluated. In multi-stage programming terminology, this is referred to as the binding time of the expression. For this, BuildIt introduces 2 new template types, dynamic var and static var. The evaluations of expressions and variables declared as dynamic var T is delayed to the next stage. This means that the generated code has the operations on these expressions as it is. This includes all operations like assignments, binary operations, and even control flow statements like if conditions and for loops that depend on these values. Here is an example of a program written with all dynamic variables and the program it would produce after first stage evaluation. Static var T, on the other hand, is used to declare variables and expressions that are completely evaluated in the current stage. Thus, the generated code has no trace of these expressions, but these static variables and expressions can be used to specialize the code that we want to generate with the dynamic variables. Let us look at an example. Here on the left, I have the implementation for the power function that calculates base power exponent using repeated squaring. The general implementation here has a control flow like loops and conditional. Now, I have declared the base to be dynamic, which means it will be an argument to the function in the generated code, and the exponent as static, which means it will be provided in the first stage. When I run this code with the exponent as 5, this is the code that we get. Notice that since all the control flow was based on an exponent which is declared to be static, it is completely evaluated here and we don't see any loops or conditionals. Now if I keep the code the same but change the static input to be 10, the code generated changes this way. If I further change it to 15, it once again produces a specialized implementation of base power 15. We will use the same principle to build a DSL compiler with optimizations from a library. Let us get an intuition of how that works. Suppose you write a domain-specific library for your favorite domain. We write this library on top of BuildIt using static and dynamic variables. Now suppose the user writes the program using the library's operators and types and executes it. Instead of running the actual program, the executable would produce a code that runs the exact same logic as the program written. Now if you stare at this carefully, you can realize that the library and BuildIt combined together play the role of a compiler, where the program written in the library is analogous to a program written in the DSL. And this is our basic idea. But you might say, generating code is only part of a compiler. What about domain-specific analyses and transformations, scheduling or tailoring the code generated for certain inputs, and what about generating device-specific parallelized code that runs on CPUs, GPUs, etc.? These are all valid concerns, and I assure you that our framework takes care of all of these. Instead of walking you through these one by one, I would like to show you a demo of how these would be implemented for a simple DSL. The language that we will build for this demo is a simple one that generates high-performance code for Einsum expressions like this: A of j equals B of jk times C of k. We will also schedule and parallelize our code for CPUs and GPUs. And finally, we will implement a well-known constant propagation parse which shows how to analyze and transform or specialize the code in a simple way. To remind everyone, an Einsum expression like this is the short for a larger expression: for all j, A of j equals summation over all k, B of j of k times C of k. Immediately, we can notice that if we were to implement a library for such a domain, we would have to implement a set of loops on both LHS and RHS. We would also have to take care of implementing the sum reduction that is implicit in this expression. A typical way to start writing this library in C++ would be to create a type for these tensors that holds the underlying buffer and the dimensions of each rank of the tensor. We would then overload all the operators, including the multiplication and the assignment operator, to implement iterating over the values and do the reductions. One simple and efficient implementation of the assignment operator could be the following, where for rank 1 tensor, we write a single loop to calculate the values for all the places. For a rank 2 tensor, we would then have to add a condition and add a 2-level nested loop to compute the values and so on. While this approach works, it is quite tedious and doesn't generalize to arbitrary dimensions. A more realistic approach would involve creating a function that iterates over the values in one rank and recursively calls the same function to iterate over the values in the next rank, and calling this function from the overloaded assignment operator. We will have to do the same for the free indices that appear on the right hand side too. This approach is pretty easy to understand and generalizes to all ranks. But this one has a bunch of recursive calls which might be harder for the compiler to optimize. Let us see if BuildIt and staging can help us with this and get us best of both the worlds. First up, here we have a simple program written in our new DSL. We have an implementation of the matrix vector multiplication where we multiply a matrix of size m cross n by a vector of size n to produce a vector of size m. For the sake of our DSL, we'll assume that these dimensions are known at compile time to better tailor our implementation for these sizes. We declare the 3 tensors with the appropriate sizes and write the Einsum expression that we want to evaluate. We also have an example of a matrix-matrix multiplication where we multiply a matrix of size m cross L by a matrix of size L cross n to produce a matrix of size m cross n. Similar to the previous case, we declare the tensors and write the Einsum expression. Let us now look at the implementation of the DSL. Just like our library, we declare the tensor type that holds the dimensions of each rank in a vector and the underlying buffer that holds the values. The only difference here is that we declare the buffer to be of type dynamic t because we want to generate code for it. Right now, we have overloaded the assignment operator and created the recursive functions for the loop on the RHS and the LHS, but we haven't filled in the loops. Let us compile and run this to see what we get. We can see that because the operators are overloaded to perform the operations with dynamic types, the appropriate expressions are produced in the generated code for both the examples. These generated expressions correspond to the Einsum expression that we wrote. Let us now go back and add the loops inside the recursive functions. Here I'll add a bunch of loops for both these functions on the LHS and RHS. We can see that we write these loops with dynamic variables because we want them to be appearing in the generated code. Let us now build and run an example to see what code we get. As expected, we now see the loop nest being generated. For the matrix vector case, we see a two-level nested loop, one for j and one for k. Inside the outer loop, we initialize the value to 0 and perform the sum reduction inside the inner loop. Similarly, for the matrix multiplication case, we see a three-level nested loop, two for the LHS and one for the RHS reduction. We can also see that unlike the code that we wrote in a library, there are no recursive calls here, just the exact loop nest as we would write for a fixed rank. This is because the rank of a tensor is known at the compile time and the recursive function is completely evaluated, getting rid of any overheads. Next, we will add parallelization to our code. For this demo, we'll first try to add parallelization just for the outermost loop, that is the loop corresponding to the first index on the left hand side. Our DSL framework supports adding parallelization for both CPUs and GPUs with a simple pragma-like annotation way, which the high-performance library writers are already familiar with. Let us go back to our implementation. We want to leave the decision of parallelization to the user, similar to the scheduling language in common DSLs. To do this, we will declare an enum device type and a static variable current device. We also modify the previously written loop to add an annotation to the first loop if this variable is set to CPU parallel. Similarly, we'll add a slightly different loop nest and a CUDA annotation if the variable is set to GPU parallel. The loop nest is slightly different because GPU parallel requires a two-level nested loop to map computations to threads and thread blocks. With this change, let us build and run our example. Once again, we get the same output. This is because even though we have implemented parallelization, we haven't instructed the DSL to generate parallel code for us in the written program. So to now enable parallelization, we will set the variables to the device that we want before the Einsum expression. For the matrix vector case, I'll set the device to be CPU parallel, and for the matrix case, I'll set the device to GPU parallel. Let us now build and run the code. We can see that for the matrix vector case, we get an OpenMP parallel loop for the outermost dimension, and for the matrix multiplication case, we get a GPU kernel that is created and launched from our implementation that performs the necessary computation. We can notice that for parallelization, we didn't have to do any IR manipulations or specialized code generation. Our framework supports parallelization with simple steps that domain experts use all the time for writing libraries. Finally, for our demo, we will show how to implement a simple analysis and transformation that does constant propagation. Before we look at the implementation, we will look at an example program in the DSL. Here we have two expressions, one that initializes b to a constant 1 and the other that performs matrix vector multiplication. If we generate the code for this program, we can see that we get a first loop nest that initializes the tensor b and a second loop nest that also uses this b to calculate c. Unfortunately, because these expressions are written separately, we end up having to load b again, even though we know it's all ones. If we apply constant propagation, we should be able to eliminate this load. To do this, let us stop thinking like a compiler developer and put on our library writer's hat. The way we would do this in our library is by adding a new variable inside the tensor type that records that the tensor is currently initialized to a constant, and that is exactly what we do. We add two variables, one to record if the tensor is a constant, and the second to record what is the constant value. The slight difference here is that we use static type to record these values because we want the property to be completely tracked and evaluated at compile time and not during runtime. Next, whenever we assign the tensor to a constant, we set is constant to true and constant val to the constant we assign to the tensor. Whenever we assign the tensor to any other expression, we reset this value to false. This is similar to providing a seed value in a data flow analysis. Now when we actually access these values, we check this flag. If the constant is set, we simply return the value we had recorded, otherwise we load the value from the buffer. Notice that so far we have done nothing different from a library implementation besides the static variable types for these variables. Let us now build and run our sample. We can see that in our generated code, the constant 1 appears directly inside of the load from B. But that is not all. There are some interesting implications to our approach. What if we modify our sample to add a loop around the Einsum expression and assign B to C at the end of every iteration? This pattern is very common in certain solver applications. Let us build and run this again. We can see that in our generated code, BuildIt has peeled one iteration of our loop and generated a different version for the first iteration that uses the constant and then uses the value loaded from the second iteration onwards. This complex transformation happens automatically because BuildIt respects the assignments to static variables and creates specialized code if it changes during the execution. Thus, we have shown with our demo how a domain expert can generate high-performance parallelized, scheduled, and optimized code by simply writing a library and without any compiler knowledge. The source code for this demo and all the components of our framework are available at these URLs. The DSL we built in this demo is a fairly simple one that demonstrates various capabilities of our framework. But BuildIt and DSL framework is not limited to such toy DSLs. In our paper, we develop and evaluate a fully fledged graph DSL that is inspired by the design of the state-of-the-art graph DSL GraphIt. We choose GraphIt because the language is rich in features both in terms of supported types and operators, and supports optimizing the generated code for variations in algorithm and input graph types. Not only this, the GraphIt DSL supports generating code for a variety of architectures including CPUs, GPUs, and some upcoming hardware like many-core and task-based parallel architectures like Swarm. Just on the GPU architecture, the GraphIt DSL provides scheduling option for load balancing, vertex set representation, direction optimization, edge blocking, kernel fusion, deduplication, and vertex set ordering. These options combined produce the largest optimization space of any graph framework, letting the compiler generate up to 576 variations for any input program. Naturally, the performance of the CUDA code generated by GraphIt is the current state of the art for any single GPU system. The compiler implementation currently stands at about 24,000 lines of C++ code, which would be difficult for any graph expert to implement and modify. We maintain a similar focus on performance while implementing the DSL with our framework. Like demonstrated before, we use the framework's annotation system to generate CUDA code and automatically move data between host and GPUs. We also further tweak the loop nest moved to the GPU kernel to implement various load balancing techniques that are critical to adapting to the sparsity in the graph data structure. We combine static and dynamic variables to perform data flow analysis, to track various properties about vertices and edges, to perform correctness and performance related transformations like inserting atomics at various places. We implement branch based on first stage parameters to implement all scheduling dimensions supported by the GraphIt and the vast space of optimization it has. Finally, we use static variables and specialization to implement kernel fusion by merging various operations into a single GPU kernel to avoid kernel launch overheads on long-running programs. All these techniques are explained in our paper with code examples and snippets. With all these combined, we are able to match the performance of the code generated by GraphIt on 5 algorithms and 9 graph inputs. But the most important aspect of this is that we are able to implement the whole DSL in only 2021 lines of C++ code on top of BuildIt, which is a mere 8% of GraphIt's GPU compiler code base. Besides being small, this implementation is like a graph library and not like a compiler, making it possible for any graph expert to use and extend as they wish. With this, I'll end my presentation. Hopefully, I've convinced you that BuildIt is an exciting new way to rapidly implement DSL compilers with low effort and little to no compiler knowledge. We have made BuildIt and all the frameworks built on top of it available open source at buildit.so. We also have an online demo on our website where you can write and build BuildIt code without having to download or compile it. If you're interested in writing DSLs for your domain, please reach out to us.